Assalamu alaikum. Today's lecture is about spectroscopy for semester 8 and the topic is pure rotational Raman spectra of linear molecules. First of all, I would like to mention the selection rules for different type of spectroscopies. For microwave or rotational spectroscopy, molecules must have a permanent dipole moment. They must be polar. For infrared or vibrational spectroscopy, the molecules must have a changing dipole. The dipole moment must change during vibration. And we had studied in the previous lecture the gross selection rule for a Raman spectroscopy, which was that the molecule must have a changing polarizability. If a molecule has a dipole moment and its polarizability also changes, then it will give microwave spectra as well as Raman spectra. It will be microwave active and Raman active. If a molecule shows a change in dipole moment with vibration and also show a change in polarizability, then it will be infrared active and Raman active. However, if a molecule is rotating and it has no dipole moment and during rotation its polarizability changes, then it will be Raman active but microwave inactive, and it will lead to pure rotational spectrum. Pure rotational Raman spectrum will be obtained in those cases where the molecule has no dipole moment, but when it rotates, its polarizability changes with rotation. Now, if we consider such molecule, a diatomic linear molecule like H2, and it is rotating, to differentiate, we consider it as H1 and H2. It is 1 and 2, 1 and 2, 2 and 1. Let us suppose it is the external electric field of strength E, which is applied to the molecule in this direction. Now we know that hydrogen molecule is anisotropically polarizable. Here it will have maximum polarizability and it will be represented by a very small ellipsoid, polarizability ellipsoid. In this direction, polarizability is maximum and perpendicularly the polarizability is less. In this case, as the electric field is at certain angle to the hydrogen molecule, to the bond axis, therefore the polarizability will be slightly smaller than the first one, and it will be represented by a larger ellipsoid. Here the polarability will become approximately 0, or it will be the maximum, as the electric field is perpendicular to the bond axis, here we will have a large ellipsoid. In the last case, we will have the same polarizability as at step 1. As this molecule is non-polar, however, as its polarizability is changing, the magnitude of the polarizability is changing as well as its direction is also changing. So polarizability can change if the direction changes or the magnitude changes. So it will be Raman active and microwave inactive, and it will produce a spectrum which will be known as pure rotational Raman spectrum. Same will be the case with linear molecules like N2, O2, Cl2, etc. These molecules will also be microwave inactive and will be Raman active, and they will also lead to pure rotational Raman spectra. We had previously discussed in the microspectroscopy, in the introduction for Raman spectroscopy, we had discussed that if E, it is an energy level, rotational energy level denoted by EI, it is the final rotational energy level denoted by EJ, and it is the virtual state denoted by V. And if electromagnetic radiations having a frequency nu excited is the frequency of the radiation, exciting radiation, and the molecules moves from the initial state EI to the virtual state V, and it falls back to the final state EF, then it will emit radiation. The radiations will have, the scattered radiation will have a frequency nu bar. Here the energy gap between EI and EF is delta E. So the frequency of scattered radiation nu bar can be written as nu excitation minus delta E. Let us suppose it is equation 1. This frequency of the scattered radiation will be less than the frequency of the exciting radiation or incident radiation, and it will lead to Stokes lines, as we had already discussed. On the contrary, if the process takes place in such a way that a molecule absorbs radiation and it moves from the level rotational energy level EF, it moves from exciting radiations E having a frequency nu excitation. Take the molecules from EF, first excited state, to the virtual state, and the molecule falls back to the initial state EI. The scattered radiations will have a frequency nu bar. Here the energy gap is delta E. In this case, the scattered radiations will have a frequency higher than the exciting radiations, and in this case we can write nu bar the frequency of scattered radiation will be given by new excitation plus delta E. Equation number 2. The scattered radiation will have a frequency higher than the exciting radiations, and it will lead to anti-Stokes lines. The Stokes and anti-Stokes lines are generally called S branch. S branch. If this exciting radiation take the molecule from EI to virtual state and the molecule drops back to the same state, we get Rayleigh lines. There is no change in frequency and we get Rayleigh lines. Now in case of molecules, the rotational energy levels, they are represented by a quantum number which is called rotational quantum number. Let us suppose we have these quantum numbers: J is equal to 0, J is equal to 1, J is equal to 2, J is equal to 3, J is equal to 4, and J is equal to 5. These are the rotational quantum numbers of a molecule. The second selection rule, first selection rule for Raman spectroscopy was changing polarizability with rotation. D alpha must not be equal to 0. Alpha is the polarizability. And the second selection rule, which is called quantum selection rule, is that delta J must be equal to plus minus 2. The transitions will only be possible if the difference between lower and upper rotational levels is of 2 units. In this case, 2 photons are used. One of the photon is absorbed and the other is scattered, and if we consider that the angular momentum of photon is 1 unit, then there will be a change of 2 units, because one photon will be absorbed by the molecules and other will be scattered. So the allowed transitions in this case will be from J is equal to 0 to 2, J is equal to 1 to 3, J is equal to 2 to 4, or J is equal to 3 to J is equal to 5. These are the allowed transitions for a molecule undergoing rotation. Now these quantum numbers represent the rotational energy levels, and the rotational energy levels are represented by the formula. The energy of these rotational levels is represented by E is equal to BHC J into J plus 1 in joules. BHC J plus 1 in joules. Now to convert it into per centimeter, we know that E is equal to h nu, which is the Planck's equation. We know that nu is equal to c by lambda. Therefore, E is equal to hc by lambda. But 1 over lambda is proportional to wave number. Therefore, we get the equation E is equal to hc nu bar. Our nu bar is equal to E over hc. Here we have equation number 3 and it is equation number 4. That is, if we divide E, putting the value of E into equation 4 from equation 3, we will get the units converted from joules into per centimeter. Therefore, we get the expression for energy in per centimeters will be, it is denoted by epsilon, is equal to BHC J into J plus 1 divided by HC per centimeter. HC will cancel out and we get the energy as BJ into J plus 1 per centimeter. Now it is the expression for the energy of rotational energy levels.